Hey folks, how y'all doing? Um, there's a couple of reminders. You have a uh, coding assignment that is due on Tuesday. Um, I put a couple of stars in here. I would like to go ahead and start receiving them by Tuesday because I've got some time off on Wednesday that I could use to go ahead and start looking at them and giving feedback on them. But given that I just got the test files up over the weekend, I will let people turn this in up through Friday with no penalty. So you can get this in as late as Friday, but you don't want this later than Friday because you're going to need your code for the exam on Saturday. Um, and I don't encourage people to be working on code on Friday night when they could be studying for the exam. So the exam is on Saturday. You would like to have your code finished early enough that you're comfortable with it and confident in how it works and have a little time to focus on the other material. So, but you do have until Friday to turn in the code on Submittee if you need some extra time. Um, as a reminder, also there is no class on Wednesday. So um, enjoy the day and try to get some rest in because that's your break, such as it is. What we're going to do today is go through about half, or a little bit more than half, of the questions on the exam to review. And if you have other questions, bring them to class or come by my office hours. I do have office hours Tuesdays at noon and Thursdays from 3 to 4. Um, and if those times are conflict with your schedule, let me know. I can meet with you at other times as well. All right. Okay, so given a permutation in two-row notation, convert it to cycle notation and vice versa. So this shouldn't be too hard. If I have a permutation in two-row notation, let's say 3, 5, 3, 4, I guess. 1, 2, 6, 5. Let's try that. Then in cycle notation, 1 goes to 3, and then 3 goes back to 1, then 2 goes to 4, and 4 goes back to 2, and then 5 goes to 6, and 6 goes back to 5. So what we're doing is we're just tracing what goes to each other. If a vertex goes back to the starting vertex on a cycle, then it's the end of that cycle. If we want to go the other way around, if we have something in cycle notation, 1, 4, 2, 5, 3, 7, 6, then I can write that in two-row notation. I see that it contains the numbers from 1 through 7. And 1 goes to 4, 4 goes to 2, 2 goes to 5, 5 goes back to 1, 3 goes to 7, 7 goes to 6, and 6 goes back to 3. So we have two different notations for the same concept. We can work with either notation, just in terms of typing your answers. Cycle notation is easier to type for sure. How do we compute the composition of two or more permutations? Well, let's go back to the example we were just looking at, 1, 4, 2, 5, 3, 7, 6. And let's say g of x is 1, 7, 2, and then 3, 4, and then 5, 6. Let's try that. So what happens when we compose f of g of x? Well, we first look at to see what happens to 1. So g of 1 is equal to 7, and f of 7 is equal to 6. And so 1 ends up going to 6. Then let's see what happens to 6. G of 6 is equal to 5, and f of 5 is equal to 1. So we go right back to 1. So that takes care of 1 and 6. Let's see what happens to 2. G of 2 is equal to 1, and f of 1 is equal to 4. So 2 goes to 4. And then we're going to repeat this logic for, the remaining elements here. G of 4 is equal to 3, and then f of 3 is equal to 7. We end up at 7. G of 7 is equal to 2, f of 2 is equal to 5. G of 5 is equal to 6, f of 6 is equal to 3. G of 3 is equal to 4, f of 4 is equal to 2, and that closes up a cycle. And so what we had here is these two functions together. We compose them together. We do G first when we compose them, whichever one is on the right. Okay. Disjoint cycles commute, and that's pretty obvious, I think. So if f of x was, say, 1, 3, 5, and g of x is 2, 4, 6, then f of g of x is 1, 3, 5, followed by 2, 4, 6, and g of f of x is 2, 4, 6, followed by 1, 3, 5. But these have to be equal because for any number, one of these cycles won't do anything to the number. For example, f of g of 1, nothing happens to 1 here, and then the 1 goes to a 3. Over here, 1 goes to a 3, but then nothing happens to the 3. And so because in each case, one of the two cycles doesn't do anything, it doesn't matter which order it doesn't do it in. There's not a, I know that sounds funny, but since nothing is happening in one of the steps, there's not actually two different operations here going on any element. It's just one operation on each element. And so the disjoint cycles commute. These are equal to each other. If we have a permutation, we can write it as a composition of disjoint cycles. We did that when we put something that was in 2-row notation into 1-row notation. But let's say we had something that was written like this. 1, 2, 3, 1, 3, 4, 1, 4, 5, and 1, 5, 2. So I've got a lot of repeated numbers in here. Can we break that down into disjoint cycles? And we can. We're going to start with this. 1 goes to 5. Start on the right. So 1 goes to 5. 5 goes back to 1. Then 1 goes to 3. And then 3 goes back to 1. So 1 is a fixed point in this permutation. Start with a 2. 2 goes to 1. And then 1 goes to 4. 4 goes back to 1. And then 1 goes back to 2. Oh, wow. So 2 turns out to be a fixed point. Let me check that again. 2 goes to 1. 1 goes to 4. 4 goes back to 1. 1 goes back to 2. I may have created a permutation that cancels itself out. Let's see what happens to 3. Nothing happens to 3. Nothing happens to 3. 3 goes to 4. No, it doesn't quite cancel it out. And then nothing happens to 4. So then what happens to 4? 4 goes to 5. Nothing happens to 5. 5 goes to 2. Nothing happens to 2. Nothing happens to 2. 2 goes back to 3. There we go. All right. So it turns into a permutation that has 2 fixed points. 1 and 2 are fixed, and then 3, 4, and 5 cycle. Okay. Given a permutation, write it as a sequence of transpositions. Well, if we have it in the form of cycles here, 1, 4, 3, 6, 9, composed with 2, 5, 7, 8, for example. We can break this down into transpositions. The 1 will transpose with, and what we'll do is now we're going to work from right to left. 1 will transpose with 9, and then with 6, and then with 3, and then with 4. Now that seems backwards, but again, we're writing them left to right, but we perform them right to left. We'll actually do 1, 4 first, and then we'll do 1, 3, and then we'll do 1, 6, and then we'll do 1, 9. So I'm writing them in the opposite order than for what we're doing them. And then over here, the same idea, 2 transposes with 8, 7, and then 5. Okay? So I'm writing them left to right, but I'm going to perform them right to left. Identify whether a permutation is odd or even. It's based on how many transpositions it takes in this form. So this is 1, 2, 3, 4, 5, 6, 7 permutations. And so this is odd because 7 is odd. Okay. Is there a way to know whether we have a permutation that's odd or even before we write all this out? And the answer is yes. But it's a little tricky. The size of a cycle is always 1 greater than the number of transpositions it takes. So this cycle has 5 numbers in it, but that's going to be 4 transpositions. And then this will be 3 transpositions. And that gives me 7. So going back even further, this is 0, this is 0, this is 2. 0 plus 0 plus 2 is even. This is an even permutation. This is 2, this is 2. That's going to be even because 2 plus 2 is 4. So I know if I have something in cycle notation, I know that each cycle is 1 more than the number of transpositions. And so I can identify whether a permutation is odd or even by looking at the cycles and subtracting 1 from the length of each cycles and then totaling up the number of transpositions that way. So we can do that. If we want to compute the conjugate of alpha by beta, so let's say alpha is 1, 3, 2, 4, and beta is 1, 3, 4 with 2 as a fixed point. Let's try that. Then beta alpha beta inverse is beta is 1, 3, 4. I'm going to leave off the 2. Alpha is 1, 3, 2, 4. And then beta inverse is 4, 3, 1. All right, so this is beta. This is alpha. This is beta inverse. We work from the right to left, and so 1 goes to 4, 4 goes to 2, and then 2 stays fixed in beta. So 1 goes to 2. Then beta inverse doesn't do anything to 2, but alpha takes 2 to 4, and beta takes 4 back to 1. And so we close the cycle. So then let's see what happens to 3. Beta inverse takes 3 to 1. Alpha takes 1 back to 3. Beta takes 3 and sends it to 4. And then 4 had better go back to 3, but let's just double check. Beta inverse takes 4 to 3. Alpha takes 3 back to 1. And then beta takes 1 back to 3. So we end up at 3. And so the composition, the conjugate ends up having 2 cycles, and so does alpha. They have 2 cycles. We say that the conjugate of a permutation has the same cycle type as the original permutation. And we haven't talked about cycle type yet, but this is what we mean by the cycle type of a permutation. This has cycle type 2,2. This has cycle type 3,1. This has cycle type 2,2. It's the number of disjoint cycles. This one here does not have cycle type 3,322. That's wrong because these are not disjoint. This would suggest that there are 3, 6, 7, 8, 9, 10 different elements being permuted, and we're actually only permuting 4 elements. We've just got a lot of repetition here. So when you're looking up the cycle type, you have to simplify this down to disjoint cycles to get the cycle type. Okay? All right. Conjugating a permutation does not change its cycle type. We just worked that out. That's one of the sort of useful things here in terms of breaking enigma. An involution. An involution is a permutation. There are a couple of ways of describing an involution. Either the composition of F with itself is the identity. We can say that F is its own inverse, which is the same sort of thing. F inverse is equal to F. We can say that the cycle type of F contains only 1s and 2s. So fixed points and transpositions. An involution is proper if it has no fixed points. Okay. The composition of 2, this is wrong. This should say proper involutions as match cycle type and vice versa. Any permutation of match cycle type is the composition of 2 proper involution. But proper is important here. I left this off of the review sheet, and it should have been there. Okay? So I've got a correction to make on number 11 here. Composition of 2 proper involutions always has match cycle type. So let's decompose a permutation of match cycle type into 2 involutions. So let's say we have 1, 3, 6, 11, and 14, 2, 9, 12, 5, and 7, okay, 13, and 8, and 4, and what number is missing? 10. So this has 14 elements, and its cycle type is 5, 5, 2, 2. So what I'm going to do as an intermediate step is to write these permutations above each other in pairs, but in reverse order. All right. And for one of the permutations, for alpha, we're just going to pair these things going down. So 1, 7 pairs up, 3, 5 pairs up, 6, 12 pairs up, 11, 9 pairs up, and 14, 2 pairs up, 13, 10, and 8, 4. For the other permutation, we're going to match up northeast, but if we have to, we wrap around within the same cycle here. We don't go over to the other cycle. So we're going to pair up 7 and 3, 5 and 6, 12 and 11, 9 and 14, 2 and 1, 10 and 8, and 4 and 13. And this permutation, I'll call it F, is equal to beta composed with alpha. So we had a permutation of matched cycle type. We broke it up into 2 proper involutions. Okay. All right. So let's talk about these different parts of the Enigma machine and how they work. I want to start with the reflector. The reflector was the only part of the Enigma machine that only passed through once. That is, the signal passed through the plug board on the way in and the way out. Passed through the rotors on the way in and way out, but the reflector was used only once per letter. But the reflector always created proper involutions. And so that's what was going on there. That reflector took these 26 letters, it reflected them, but that it only did involutions. If Z went to W, then W went back to Z. So the rotors, there were slots for different rotors, and we had more rotors than slots. So we could use a subset of those rotors each day. The rotors would rotate on a gear, but they also had a pin that would advance the next rotor once a rotor had completely cycled around. But the pin position was adjustable. So adjustable pin positions. And they would advance when you hit the key before the encryption. So the rotors would rotate before each encryption. And then finally we got to the plug board. The plug board also created involutions, but maybe not proper. So also was an involution. Maybe not proper. The reflector was always proper. The plug board was maybe not. And it just had a sequence of wires that you would connect one letter to another letter. So just had 26 sockets and up to 13, but in practice, but usually around 10, connections. Okay. Which parts of the Enigma machine were adjustable? The operator could adjust the plug board. And the rotors, it would take a trained technician to operate the reflector, to adjust the reflector. So, in essence, all parts of the Enigma machine were adjustable, but we could adjust the plug board and rotors on a day-to-day basis. We had to adjust the reflector on a more planned schedule because we had to have a trained technician to do that one. Prior to 1940, messages had a separate ground setting and a message setting. How is this message setting transmitted? Twice at the beginning of each message. Using the ground setting to transmit it. Show that each Enigma permutation was a conjugate of the reflector and deduce what the cycle type of each permutation was. Well, you ended with the reflector. Well, not ended, but this was in the middle. And you went through the rotors. Let me careful how to draw my arrow. So you started with the keyboard. You went through the plug board. And that would create an encryption. So whatever key you typed on the keyboard, you got P of that letter. Then you went through the rotors, and there were 3 rotors. R1, R2, R3. So then the rotor would encrypt what was on the plug board. The second rotor would encrypt that. The third rotor would encrypt that. Then you went through the reflector, and the reflector would encrypt all of this. But then it came out of the reflector and went backwards through these rotors. So we would get an inverse of the rotor transformation, an inverse of a rotor transformation, an inverse of a rotor transformation. And then finally, it would go backwards through the plug board, which would get me an inverse of the plug board transformation. Well, this and this are inverses of each other, and so this is a conjugate of the reflector. And because the reflector could only create a proper involution, the cycle type of the permutation was, there were 26 letters, and they got adjusted in 13 pairs. So 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2, 2. 13 twos was the cycle type of every permutation that Enigma could ever create. All right. How does Rejewski's theorem capitalize on 15 and 16? That if we had a plain text that was, for example, ABC, ABC, and the Enigma would take this and create ciphertext, but the rotors would turn each time. And so what would happen is we would have some permutation that would give me K1 of A, and then this permutation would be a little bit different because the rotors would be in a different position. So I'd get K2 of B, K3 of C, and K4 of A, K5 of B, and K6 of C. But let's suppose that K1 of A was some letter and K4 of A was some other letter. Then what we know then is that K4 composed with K1 of X is equal to Y. K1 would send X to A, and then K4, because it was an involution, had to send A back to Y. And so how does Rejewski's theorem capitalize on this? That we would know that K1 composed or K4 composed with K1 actually doesn't matter which order we write them, and I'll go ahead and leave K1 composed with K4, K2 composed with K5, and K3 composed with K6. These can be observed entirely from the ciphertext. And all are of matched cycle type. And since there are only a small number of ways of breaking up a permutation of matched cycle type into a pair of proper involutions, we had small enough possibilities for K1, K4, K2, K5, K3, and K6 by the end of a day that we could attack the problem by brute force. We wouldn't necessarily have an exact answer, but we had a small enough number of cases that if we assigned, cases to teams, we had enough teams that we would eventually be able to break a message over the course of the day. It didn't happen quickly. It still took many hours for this process to play out, but this was doable. So what we're going to look at, we've got some more reviewing to do. The next review is going to include Japanese encryption, and then AES, and then computation in our finite field. All right. Thanks for watching. I'll see you again on Friday.